Hey, ready to do a little math? Here we go. So week 5, we're playing around with radical equations, Pythagorean theorem, complex numbers, and then we're going to start chapter 4 and take a look at quadratic functions. So radical equations. So those are any kind of equation that has a square root or a cube root or anything like that in it. So for example, consider square root of x plus 2 equals 11. So in order to solve this, I have to get the x alone, and there's two problems here. There's a plus 2, and the x is in the square root. So when you're solving an equation, you get rid of the things furthest from the x first. So I would subtract 2 from both sides. And so that's going to leave me the square root of x equals 9. Now, I got rid of the plus 2 by doing the opposite, minus 2. The opposite of taking a square root is a square. So next thing I want to do is square both sides. And always use parentheses to be safe. So if I square a square root, that ends up canceling. So that's just x on the left side. On the other side, I square 9 and I get 81. So it looks like 81 is the answer here. You can kind of think about it and check. What's the square root of 81? Well, it's 9. 9 plus 2 is 11. So it looks like this is going to check. I'm going to get to do some more complicated ones. So consider the square root of x plus 8 equals x plus 2. Now, there's an important observation I can make about the previous example. Before I'm ready to square, I have to get the square root alone. So it wouldn't be useful to square at the stage when it's blue here. I have to get rid of that, anything outside of the radical, and then I can square it. So here, it turns out there is nothing on this side of the equation outside the radical, so I really am ready to square. But you always want to think, before you square, isolate a radical and square both sides. Now, squaring technically is multiplying a number by itself, and when I multiply a square root by itself, it cancels the root, leaving what's inside. So there is an intermediate step here that says take the square root of x plus 8 and multiply by the square root of x plus 8. Now that nicely cancels the root, so I just get x plus 8 on that side. The other side, I have a little bit more work to do. I have to take x plus 2 and multiply by x plus 2. So x times x is x squared. X times 2 is 2x. 2 times x is another 2x. And 2 times 2 is 4. So x plus 8 is still hanging out there. Cleaning up the right side, I get x squared plus 4x plus 4. And then, since I have a square, I'm thinking of the zero product rule way back from our first chapter. So I would bring everything to the right side. So I'm going to subtract the x. I'm also going to subtract the 8. And I'm lining up like terms when I do that. So x minus x is 0. 8 minus 8 is 0 on that side. And on this side, I get x squared plus 3x minus 4. And then I hope to factor it. So I'm going to factor by guessing, because it's a 1x squared, because that's going to be x times x. 4 is either 2 times 2 or 4 times 1. And 4 minus 1 is 3. So I'm going to go 4 here and minus 1 there. Positive times a negative is a negative. 4 minus 1 is 3. That looks good. So I'm trying to solve for x here. So I have to use the zero product rule so I can split it based on the product. So either x plus 4 is 0. So x could be negative 4. Or x minus 1 equals 0. So x could equal 1. Now I still need to check both of these to make sure they work. So I'm going to go to a new screen. I need to check inside of x plus 8 and the root does that equal x plus 2 when I plug in different numbers? So first number I came up with was -4. And I have to plug it in and see what happens. So this is going to give me the square root of -4 plus 8. And I'm hoping that equals -4 plus 2. So on this side, let's see, -4 plus 8, that's 4. And the square root of 4 is 2. On the other side, -4 plus 2 is -2. Uh-oh, doesn't work. So this is not a solution. Sometimes when you solve these kinds of equations, you get extraneous solutions, meaning they don't work in the original, but they might work in some intermediate step. All right, so I also need to check x equals 1. 1 plus 8 there, question mark, does that really equal 1 plus 2? That's the square root of 9, which is 3, and 1 plus 2 is definitely 3. Okay, so that one checks. So coming back here, I can go, that's not a solution. It doesn't check, but this one does. So I only get a single solution. It depends on the equation. Sometimes all of the solutions will check. Sometimes only one of them will check. Sometimes none of them will check. It's possible there are no solutions to some equations. That's 3-4. You're going to have some fun there. Let's take a look at 3-5 and 3-6. Pythagorean theorem, distance, and midpoints. So I'm going to pick a problem from your homework to take a look at. So here I have a problem. I want to find the distance between the point -5, 13 and 2, -19. So I'm going to screenshot that sucker. All right, so in a problem like this, it's a really good idea to graph them. So I'm going to plot these, and let's say I let every other one of these marks be equal to 2. So this would be 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, 6, 8, -10, and 2, 4, 6, 8, -10. So that'll give me a rough idea where my points live. All right, so I need to plot -5, so go down over 5, excuse me, and then down 13. So 10, 11, 12, 13, that's going to be right there. And 2, -19. So can I do that? 2, 4, 6, 8, 10. So down here would be -20. So 2, -19 would be about right there. So I need to find the distance between these 2 points. So the distance from here to there. Now, a cool thing about that, if I think about that as a line with a slope, it has a rise and it has a run. And when I make that triangle, I get a right triangle. Right triangles are nice because that is the Pythagorean theorem. So it turns out the Pythagorean theorem is the way you find distance. So here I need to get from -13 to -19. And so that is a rise of what? -6. In the run, I had to get from -5 all the way over to 2. So that would be a run of 7. Pythagorean theorem says if you have a right triangle, and these adjacent to the right angle are called the legs, and this long side is called the hypotenuse. Usually label that C. It says if you take the lengths of the legs and square them, and then add them up, you'll always get the length of the long side, the hypotenuse. So in this case, I'm going to have to square -6, and I'm going to have to square 7, and that's going to give me the square of the long side, which is the distance I want. Right? That's the C here. So that's going to be 36 and 49. It's C squared. So what do we get there? Let's call that 50, 60, 70, 85 is C squared. So C would have to be the square root of 85. Now, technically, it could be the negative square root of 85, but this is a length, so it's got to be the positive one. Next thing I want to check is if I can clean up the square root of 85. So I'm just going to do a quick factor tree on that. So let's see, 85. 5 goes into 85 how many times? 5 goes into 8 once with 3 left over. 5 goes into 35, 7. So it's 5 times 17. 17 doesn't factor. Neither 5 nor 17 is prime. So it turns out the simplified exact answer is the square root of 85. I should get an approximation on that too. It's good to have both to see if that distance makes sense. So let's see, SQRT of 85. And my calculator says that's about 9.2-ish. So does that seem like a reasonable answer? About 9.2. Well, this length is 6, that one's 7. This is the long side. It's got to be longer than 6 or 7. 9.2 is a little longer, but not too much longer. That seems reasonable. So I think this is a pretty reasonable answer. I like it. So I'm going to go with it. The question is, does the online homework want an exact answer or an approximate answer? Find the distance between the 2 points. Enter a mathematical expression. Looks like they want an exact answer. So I would type SQRT of 85, close the parentheses. Syntax okay, and they're also telling me that is approximately 9.2-ish, again, which seems reasonable. Nice work. Okay, so be careful as to whether it says exact or approximate. So here it says enter a mathematical expression. If it wanted the number, it would say enter a number or a decimal. All right, so Pythagorean theorem is a distance formula. So summarizing that, if I have 2 points, this one, and I call this point over here x1, y1, and this one over here x2, y2, I want to find the distance in between them. Well, that makes a right triangle. So I need to find the rise for that triangle and the run for that triangle. The rise is always the distance between those two y values, so y2 minus y1. The run is always the distance between the x values, x2 minus x1. Pythagorean theorem says square each of these lengths. So I'm going to take my y squared minus, my y2 minus my y1, square it. So that's the length of this side. Pythagorean theorem says square the length of the other leg. So add that on to the square of the other length of the leg, x2 minus x1. And that will give you the square of the distance here. So let's call that d for distance. So that equals d squared. Now, I don't want d squared, I want d. And so the trick there is I take the square root of both sides. And there you have it, the distance formula, because when you square root a square, that gives you whatever was inside d. So the distance is always that rise squared plus the run squared, and then take the square root of all of that. There's your distance. Midpoints are pretty easy. If you find the average y value and the average x value, that gives you the midpoint between them. Average would be add them up, divide by 2. So picture does 1,000 things. So as far as midpoint, I highly recommend anytime you're given points, graph it. Makes the problem 10 times easier. The midpoint is always going to be x2 plus x1 average, y2 plus y1 average. All right, have fun with that stuff. Moving on, complex numbers. So in the beginning of this chapter, I mentioned trying to take the square root of -1. And the question is, what number is that? I put a question mark here, and I square both sides. If I square a square root, I get what's inside. So I'm looking for a number whose square is -1. And it turns out that's not any of the regular numbers we're familiar with. So we're going to make a new number here to fit this description. That new number is called I. So two ways to look at I. I, as a number, is equal to the square root of -1. If you square I, then you get -1. Okay? I times I is -1. That's basically what I'm getting from up here. So this is a relationship you got to memorize. Sometimes I is called the imaginary unit. Unit because it is one. Imaginary because that's some stupid name somebody came up with a whole long time ago. We really should get rid of that, but I'm stuck with it for now. When we take real numbers and imaginary numbers and stick them together, we get complex numbers. Oops, wrong button. So a complex number is a number like 2 plus I. It's a combination of a real part and an imaginary part. Now, that really means 2 plus the square root of -1. And since 2 doesn't have a square root of -1, they aren't like terms, and this is the best I can do to add them. So if somebody says add 2 to I, you just did. You can't simplify it. So complex numbers are numbers that are a little more complicated. So this is a lot like things we played with earlier in the course, 2 plus the square root of 3. Okay? We can add, subtract, multiply, and divide things like this. We just can't take 2 plus the square root of 3 and make it any simpler without using a calculator and getting an approximation. So let's take a look at subtracting two complex numbers. Suppose we had 2 minus 3i, and we want to take that away from 4 plus 7i. Addition is pretty straightforward. Add like terms. Subtraction, we have the step of distributing that subtraction first. So this is really the same as 2 minus 3i minus 4 minus 7i. 2 minus 4 is -2. -3i's take away 7i's gives me minus 10i's. So you can subtract complex numbers. You can add complex numbers. You can even multiply and divide them. So if I have 2 plus 3i times 3 plus 2i, I have to distribute. 2 times 3 is 6. 2 times 2i is plus 4i. 3i times 3 is plus 9i. And 3i times 2i would be plus 6i squared. Trick. I squared is really what? You got it. It's -1. So this is really 6 times -1, or -6. So I have some real numbers and I have some imaginary numbers. Coincidentally, 6 plus -6 is 0, so I have no real part. 4i's plus 9i's is going to give me 13i's. So I can simply say the product here ends up being just 13i. The real part disappeared. Sometimes it'll disappear, sometimes it won't. Now there are special numbers called conjugates that were mentioned in a previous section. And conjugates are numbers that have a different sign in the middle, addition versus subtraction. So for example, 2 plus 3i versus 2 minus 3i. Those are conjugates. Or -3 minus, oops, wrong button, minus 5i. Its conjugate would be -3 plus 5i. And an amazing thing happens when you multiply two conjugates. So I'm going to take my first pair. If I take 2 plus 3i, and I multiply that by its conjugate, 2 minus 3i, This is basically related to our difference of two squares formulas. The middle terms are going to vanish. That's going to give me a 2 times 2, and then a 2 times negative 3i. A 3i times 2, and a 3i times negative 3i, which will be a negative 9i squared. Now, because these just differ by the sign in the middle terms add up to 0, so they disappear. That leaves me with 4 minus 9i. Another cool thing here, it's 9i squared, sorry. Anytime you square I, you get negative 1. So this is really 9 times negative 1, or actually negative 9 times negative 1. So that cleans up to be 4 plus 9, which is 13. So anytime you multiply a pair of conjugates, what that gives you is a real number. I goes away completely, as long as the two numbers are conjugates. Plus changes to a minus, or the minus changes to a plus. So complex arithmetic you're going to get to play with in sections 3.7 and 3.8. Then you're going to move on to section 4.1 in chapter 4, quadratic stuff. So quadratics are things like y equals x squared. Anytime you have a square variable in there somewhere, it's a quadratic. So we started off playing with quadratics like x squared minus 2x minus 35. And sometimes these quadratics are factorable. Now, by looking at equations and functions, we're going to take a look at a couple of things. One, what does it look like when you graph these things? The graphs turn out to be what are called parabolas. And then what happens to the ones that aren't factorable? If they're non-factorable, then you're going to develop a thing called the quadratic formula, which you may have seen before, and another technique called completing the square. So an equation doesn't have a factorable quadratic, then it turns out there are ways to solve it sometimes when factoring fails. So that's completing the square in the quadratic formula. So first, just let's take a look at y equals x squared. So I'm going to get a graph going here. So let's put an axis right there, and another one right here, say. Close enough. And let's mark those off. 1, 2, 1, negative 2. This could be negative 1, 1, 2, 3, 4. This is my y-axis, and this is my x-axis. So to graph a quadratic, the easiest way to do it without a lot of experience is to make a table of values, x and y. And so I'm going to pick negative 2, negative 1, 0, 1, and 2 to plug in to this equation right here. So if I square negative 2 times negative 2 is positive 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. And so I can plot those points. Negative 2, 4. Negative 1, 1. 0, 0, 1, 1, and 2, 4. And connecting the dots, I get this U-type shape that's roundish at the bottom and heads up and to the right on one side, up to the left on the other side. Let's view that in Desmos. So I just want to type y equals x raised to the second power. And so I get this nice graph here. And as I zoom in on the bottom, you can see it's got this nice rounded shape at the bottom. So that shape's called a parabola. Cool thing about a parabola, if you were to take this shape right here and rotate it, let's say we spin it around the y-axis, we get a bowl. And that bowl is the shape of a dish, like you would receive satellite dish. And you already have dish TV or used to. Satellite dishes are three-dimensional parabolas. And they have some wicked cool special properties. Let's graph another one. So earlier I had typed x squared minus 2x minus 35. And somewhere here lives that sucker. Oh, there it is. It's way out there. Okay, let's zoom out some more. Actually, let's change the scale. We need to go down lower. Let's take y down to, I don't know, negative 30. Oh, negative 50. Should be far enough. All right. So this is that parabola. And notice it has a couple of places it hits the x-axis. It has a place it hits the y-axis, and it has a minimum point. Some parabolas are upside down and will have a maximum point. I just want to play around with this one a little bit. So, new page. Let's grab that picture. Okay, so this is a graph again of the equation y equals x squared minus 2x minus 35. Now note, this factors. So I could factor it as x squared is x times x. 35 I'm going to look at as 5 times 7. And to get a negative 2 in the middle, the 7 has to be negative and the 5 has to be positive. So here's another way to write this equation. So here I have the equation in factored form. The top version is what's called standard form. Now the standard form is kind of cool right here, because this number right here is my y-intercept. And notice this point down here is the point 0, negative 35. Okay, so the standard form tells me the y-intercept. This one right here is called factored form. And the factored form is kind of nice because the factored form tells me the x-intercepts. Right? If I set this equal to 0 and solve, that means I get x plus 5 equals 0. So x would have to be negative 5. I also get x minus 7 equals 0. So x would have to be 7. Now, it's hard sometimes to just look at this because I got to change the signs to get those intercepts, but there those intercepts are. Now, another cool thing about knowing those intercepts is the number right between them. So if I find the average value of negative 5 and 7, well, that means just take negative 5, add it to 7, and divide by 2. Negative 5 plus 7 is negative 2 over 2. Gives me a, let's see, did I do that right? No, a positive 2, which gives me a 1. And since these were x values, that is x equals 1. And if I draw the line when x is equal to 1, that's this line right here. I believe it's straight. It splits this parabola in half. So that's called the axis of symmetry. And on the axis of symmetry is a special point right here, and that point is called the vertex. One way to find the vertex is if you have the x-intercepts, find the average, the number in the middle of the x-intercepts. That's always going to be the x value of the vertex. To find the y value, you got to plug that back into your equation right here. So the y value would be 1 squared minus 2 times 1 minus 35. So that would be 1 minus 2 minus 35, which is going to give me negative 36. So the vertex here is 1, negative 36. So the vertex is usually a lot of work to find. No big deal. But it's an important point. It's the turning point where this graph is dropping for a while, and then it starts to rise. So the vertex represents the place that it turns around. And so that is an important number. Now, the idea of transformations came up in the beginning of chapter 3. Transformations are if you start off with a function let's say x squared, but it could be the square root of x, and you do something like make a new function by replacing the x with an x minus 2, what happens to the graph? And we learned in section 3.1 that if we replace x with an x minus 2, that will end up being a shift to the right by positive 2, kind of the opposite of what I would expect to happen. Now, an interesting thing about this graph right here, this parabola right here has exactly the same shape as this parabola right here. Now, not all parabolas have the same shape, although they're all like a U. For example, this one right here, if from the vertex I go right 1 and up 1, there's a point. If I go right 2 and up 4, there's another point. Notice that this graph over here, if I go right 1 and up 1, I'm going to get a point. Right? Here I'm at the point 1, negative 36. If I go left 1, up 1, I'm at the point 0, negative 35. Okay? I could also go over 2, up 4, and I'll have another point on the graph. So this has the same shape as y equals x squared. That means it's just a transformation of it without stretching or compressing it. The transformation is the vertex used to be over here. I shifted right 1 and then down, 36. So my claim is that I can reproduce this graph by, instead of calling it y equals x squared minus 2x minus 35, I can write it as a transformation. So if I want to shift y equals x squared to the right, I would replace the x with an x minus 1 to shift it right 1. If I want to drop the whole thing down 36, I would take away 36 out here. So this right here means go right every point, go right 1. This one right here means every point needs to go down 36. Okay, so I'm going to check that out in Desmos, see if it's true. Here we go. So I'm going to graph a new function. Desmos will give it a different color. I want to graph y equals parentheses x minus 1 squared. So that shifts it right 1. Okay, see that over here? I don't want to drop that down. So arrow right to get out of the power, minus 36. And I should see the green line sits right on top of the blue line now. Exactly. I turn off the green line, you'll see the blue line. Turn off blue, put the green back in. They are the same function. So this is another form of a quadratic equation called the vertex form. And there'll be more on that later. So that's an intro to about half of chapter 4 and half of chapter 3. Have fun, do good math, stay in touch.